So we just finished up the moles unit in chemistry, and that was looking at how do we convert between grams of a substance to moles and to how many atoms that is. What we're going to start doing now is looking at chemical reactions more in depth. And in order for us to understand chemical reactions, we have to understand how to balance out and write generally these chemical reactions in their balanced form. And the reason we do this after moles is because moles are involved in a balanced chemical reaction. And so when we look at balancing chemical equations or reactions, the first thing we need to know is what is a chemical reaction? And so what a chemical reaction is, as a reminder, is when you take one or more substances and turn them into something new. So that could be one or two new substances, depending on the reaction. But as you're doing that, you have to follow something called the law of conservation of matter, which says you cannot create or destroy atoms. So a lot of students, when they take chemistry, they think that you can take, for instance, a oxygen atom and turn it into gold. Now that is more something that we call alchemy, right? Which is what you think of like potions and witches and all that magic stuff. Unfortunately, I have not found a way to do that yet. So if you do, let me know, because that would be great. Chemical reactions do not proceed that way. They follow the law of the conservation of matter, okay? And the law of the conservation of matter says that we can't create or destroy new substances. We can only rearrange what's already there. So if you think about Minecraft or you think about Legos, right? You can't change the individual blocks or Legos, but you can change the way that they're arranged with other Legos or blocks and make new things from that, okay? So when I look at my reaction here, right, what we call this left side of the arrow here is we call that these are the reactants. And to the right, we have what we call our products. Now, between the reactants and the products, what you should notice is that there's the same number of irons on either side of the arrow, meaning that the 4 iron atoms that are there in the beginning of the reaction are there at the end as products. Same thing with these oxygens here. There's the same number of oxygens in the very beginning than there are at the very end, okay, if I count these all up. Okay, so in looking at this, right, what we'd expect is over the course of the reaction, the number of each atom to stay the same. So a chemical equation shows you the relative number of atoms, molecules, or formula units that you can use to react and form whatever you want, whatever substance you're looking at. So in the case of this iron and oxygen reaction over here, right, we can say that there needs to be at least 4 iron atoms with 3 molecules of oxygen, because these come as what we call diatomic molecules. They come in pairs of 2, to make 2 formula units or groups of that iron 2 oxide, iron 3 oxide, okay? So that's the minimum number of atoms. But if we're thinking larger scale, right, we want to make more than just a couple atoms of these substances. We use the unit of a mole from last chapter. So a mole is a group of 6.02 times 10 to the 23rd atoms, and that's more so a visible quantity of the substance. So you can also think of these coefficients as the number of moles of each substance it takes to make your particular product, okay? So that's typically how chemists think, and they predict how much of each reactant you need to make how much product. So if you think about like pharmaceutical companies and other things, they need to know how many moles of each thing to put into the reaction to make their quantified product, okay? So this is more so what we're looking at is number of moles representing those coefficients, okay? So if we look at another example, here's water and oxygen and hydrogen here. So we have the reactants of 2 moles of hydrogen and 1 mole of oxygen, making 2 moles of water, which is about 36 grams. Okay, so that's a decent amount of water that we'd be able to see with the eye. Okay, so how do we balance these equations? Well, what's really important is give yourself a star here. I always tell my students in class to star this. When you do this, you cannot change the subscripts, okay? Those are used to make substances electrically neutral. So here, this little subscript 2 cannot be changed. But what we can change are the coefficients that come before the chemical, okay? So that big 5 in front of the H2O can be changed to balance out a chemical reaction. So here are your general steps for balancing. If I give you words, something like water instead of H2O, okay, you got to turn those into chemical form, in symbol form, before you go ahead and try to balance. In this screencast and these notes, I'm only going to give you the formulas, okay? And then once you do that, you can count up the number of particles of each type and make sure that they're the same on either side of the equation. And then finally, place those coefficients to make sure unbalanced elements are in balance, and repeat this process until you're done. Okay? So let's take a look at this first one involving H2O to see if we're good on this process. So the first thing that I do is I take a look at how many H's are on the left, and I have 2 right now, and I have 2 O's. I also have 2 H's to the right, but I only have 1 O. So to balance this out, I need to adjust my oxygens, and I can only do that by using a coefficient. Now, a lot of students would be tempted to put a little 2 here to balance this out, but this now has become hydrogen peroxide, which is a poisonous liquid that you cannot ingest. So we've changed the substance. That is not how we balance equations. What we do instead is we use a big 2 in front, and that 2 changes the number of oxygens. So this is being multiplied by that hidden subscript of 1 underneath the oxygen, giving us 2. Okay? But kind of like in life, when you may adjust one thing, something else comes out of balance. In this case, the hydrogens have now multiplied by 2, and there's 4. But it's not that hard to change. If we just go to the left side of the arrow and we add a 2 in front of this H2, now we have that proper number of 4 hydrogens and 2 oxygens on either side. Now, to finish this problem, you can put a 1 in front of the O2, or you can leave it blank. Typically, in a chemical equation, we won't write coefficients of 1 in front of chemicals, so you're free to write either 1 or keep it blank in front of coefficients of 1. All right, example number 2. Okay, example number 2 is a little bit more difficult. What we're going to do for example number 2 is we're going to do the same thing. So we're going to start with 1 of each substance to start on the left, K and Cl, and we have 2 O's. Now, on the right side, we have 1K, 1Cl to start, and we have 3 O's, okay? When we do this, okay, now we got to adjust and start by adjusting things that are out of balance. In this case, it's the O. So right now I have 3 O's on this side and 2 O's over here. Kind of like we did in formula writing, we have to find the least common denominator between those two, which is going to be 6. So we need to get each side to have 6 oxygens. To do that on this side, I'm going to add a 2. That puts it to 6. On this side, I'm going to add a 3, make this 6. But now, remember, by adjusting this oxygen, I also have to adjust my number of potassiums and chlorines. So now there's 2 of each of those on this side, which means I have to put a 2 here to finish out my problem. Okay, so here are some tips that I suggest students to follow as they're getting stuck or if they get stuck. First thing you want to do is you want to balance hydrogen second to last and oxygen atoms last. These will often fix themselves if you follow this method. So to highlight this tip, let's look at example number 3. Okay, this is what I like to call in class a Cho equation. In reality, it's called an organic combustion. And it's basically the reaction behind burning things. So when we burn things, we add oxygen to it. Okay, so any hydrocarbon, which is carbon and hydrogen together, plus oxygen will always make water and CO2, which is the burning chemical reaction. So here, what I mean by balance carbon first, hydrogen second to last, and oxygen last, is you should balance these elements in that order, and usually things will work themselves out in the end. Okay, so what that means for you is I'm going to start by balancing out and taking an inventory. So I have 3 C's, I have 8 H's and 2 O's on the left. On the right, I have 1 C, I have 2 H's, and I have 3 O's on the right. Okay, now why is it 3? You have to count both groups of O here that I have in purple. So that's really, really important that a lot of students sometimes forget. Okay, so in looking at this, let's take a adjustment here that we need to make. And let's make this carbon 3 on this side by adding a 3 in front of the CO2. After I do that, now I'm going to focus on hydrogen. I'm not going to worry about oxygen yet. I have 2 H's to the left, to the right, and I have 4 H's to the left. So what I'm going to do is I'm going to make this 8 by putting a 4 in front of hydrogen. So the final thing that I have to do now is I have to figure out this oxygen situation. Okay, so I have a 3 times a 2, which gives me 6, and a 4 times a 1, which is a hidden subscript of 1 to give me 4. That means that I have 10 oxygens right now. So to adjust that to the left, I'm going to put a 5 in front of O, which would give me 10 oxygens. Okay, and then if you want, you can finish off that 1 there. Okay, last but not least, let's take a look at tip number 2. tip number 2 here is going to say to keep polyatomic ions together when balancing to show if they show up on both sides of the equation as that polyatomic ion, okay, rather than breaking them into their individual atoms. So what I've done here is I've put a box around my polyatomic ions in this equation. And so instead of breaking them into sulfur and oxygen and nitrogen here, I'm going to keep my sulfate group, what I have over there. I'm going to keep the sulfate group as one thing, and I'm going to keep this nitrogen group as one group, nitrate group as one group, instead of splitting them into their individual atoms. Now what I can do is I can count up how many of each I have using those polyatomics as groups. So here, I'll start and I'll say that there's 2 sodiums, there's 1 sulfate, there's 1 calcium, and there's 2 nitrates. Okay, I'm going to do the same thing on this other side. I have 1 sodium, I have 1 sulfate, I have 1 calcium, and I also happen to have 1 nitrate. So when I have polyatomics in my equation or my reaction, what I'm going to do is I'm typically going to look at the metal component of whatever I'm looking at first. So I'm going to look at the sodium here, okay? And I'm going to balance the sodium that's in front of one of the polyatomics first, okay? Because calcium's already balanced in this equation, I'm going to look at the unbalanced metal first. So in this case, it's sodium. So what I'm going to do is I am going to change this to I'm going to change this side to a 2. The way I'm going to do that is I'm going to add a 2 in front of the sodium. Now, I happen to also affect the nitrate number and make that a 2. And if I look carefully, right, by adding just a single 2 and balancing out that sodium, my nitrates happen to work out just fine. And now I have the equal number of nitrates on either side. Okay, because 2 times the nitrate gives me 2. All right, and then the rest of these you can fill in as 1s. Okay, let's look at what I call a spicy one. Now, the spicy one is going to use this last bullet point tip here. And that last bullet point tip says, if all else fails, multiply every coefficient in the equation by 2 and try to balance again, okay? Spoiler alert, this is going to be an all else fails. And these all else fail scenarios only happen on these CHO equations, these equations that have C, H, and O only in them, these organic combustions. Okay, so let's look at this CHO equation. Right now, we have 4 C's on this side, 10 H's on this side, and 2 O's over here. Over to the right of the arrow, I have 1 C, I have 2 H's, okay, and I have 3 O's. Okay. So let's go ahead and start making some adjustments. So the first thing I'm going to do is I'm going to add a 4 in front of the C to give me 4 to balance out that carbon. Then I balance hydrogen second to last. So that means that I need to put a 5 in front of the H2O to make this 10. And then finally, this is where we have a split oxygen scenario again. So I'm going to take a look and see what happens with this split. So right now I have an 8 oxygens from that CO2 group. And I have 5 from that H2O group. So that means I have a total of 13 oxygens here. And this becomes an issue because if I look at my oxygen number to the left in my reactants, I only have 2, and they're going to come in groups of 2. So if I were you, what is the number that I'd want to put in this blank here to make this equal to the number of oxygens in the products? Go ahead and take a minute to think about that. Okay. So if you think about what is 13 divided by 2, because that would be about 6.5. So if I were to multiply oxygen by 6.5, that would get me to 13. Unfortunately, we are not allowed to have decimals in our coefficients of a chemical reaction. So what we have to do is we have to use the all else fails scenario. And what that involves is us multiplying the entire equation by 2. So remember that this blank is just a hidden 1. If we have to use a decimal to balance out the reaction, if there's some like weird prime number of oxygens on the right product side, what we have to do is multiply everything in this equation by 2. So we're going to take all of our coefficients and we're going to multiply them by 2. So when I do that, this one will become a 2, this one will become a 13, this one will become an 8, and this one will become a 10. So now we can reevaluate and see if it works after this all else fails rule is used. So here, now on the left, let's start with the reactants. We have 8 carbons, 20 hydrogens, because now we have 2 times 10 there, and we have 13 times 2, which is 26 oxygens. Okay. Over here to the right, we have 8 times the carbon, which gives us 8 carbons. We have 10 times 2H, or H2, which gives us 20 hydrogens. So it's looking good so far. Now, here's where it gets tricky, is we have an 8 times this 2 here, which means that this is really 16, okay? And we have a 10 times this hidden subscript of 1 here, which means we have 10. So now we have this 16 plus 10, which gives us 26, okay? And that is what we were looking for to balance our oxygens. Okay, one last try here is we have this C2H5OH, so we have another CHO equation, and this is another spicy one for a slightly different reason. Now, question I want you to ask yourself, and I want you to answer, is can we box this OH in here and group it up? Meaning, can we box it and consider it a group like we did in this problem up here? So I want you to think about that for a second. Okay, so the answer you should have gotten there was no. You can only group polyatomic ions when they're on both sides of the equation. So hydroxide is a polyatomic, but you can't group it because it's not on the reactants, the product side, and the reactant side. So we have to just do our standard CHO here. CHO, CHO. Now what we're going to do is we are going to start by taking our inventory. So we have 2. Now we have a split H here, but that's going to be 6. And then we have a split O as well, which gives us 3. Over here, we have 1 carbon, we have 3 oxygens, and we have 2 hydrogens. So we're going to start with our carbons, okay? That means that we're going to put a 2 in front of the CO2 to give us 2 Cs, all right? After we do that, let's focus on the H's, okay? Right now, I said we had 6 H's to the left in the reactants, so we need to make the 6 by putting a 3 here. Now we have a split O group again, so that's going to be 4, and then this is going to be 3, okay, because it's a 3 times that hidden subscript of 1. So that means we have 7 total oxygens here. Now, this seems like it's going to be tricky because we have a 3 and a 7. So here's my hint, though, is over here, it looks like I have 1 oxygen, okay, and I need to get to 7. So I need to think about what number plus 1 is equal to 7. Well, that number would be 6. Can we get 6 from this pair of oxygen group here? Well, yeah, if I just add a little 3 in there. So if I add a 3 there, this will give me the 6 oxygens that I need because I'm going to do that 3 times 2. And I have the remaining oxygen in that hydrocarbon here. So that will give me my number of 7 that I'm looking for. So whenever you have a single oxygen here and a split oxygen here in pairs, typically speaking, that pair will allow you to get the number of oxygens you need. Okay, so this is then the point of class where I'd have you guys take a look at these and try these on your own for homework. Okay, so whenever you're back in class, check with Mr. Hopkins and see if you can get the key here. All right, bye.